Hi, welcome to the dynamics tutorials. So for this problem we are also going to have an equations of motion approach. We're looking at normal and tangential coordinates, and this will be a kinetics problem, so we'll be looking at force and acceleration. So we have a racetrack that has a circular portion that's going around this middle portion here, and the radius of the circular racetrack is 200 meters. The racetrack has some kind of banking angle theta to make it easier for the cars to come around, and we want to find what that banking angle is such that no friction is required to maintain the car on the track, but we have to give a speed, and so this is a speed of 45 meters per second. So let's take a look at our coordinate system, because this is probably the trickiest part of this problem. So your tangential direction is going out in the direction that the car is coming. So it's coming out of the board or out of your paper towards you in this direction. The normal direction is going in towards the radius of curvature. So imagine that this is a big circle here. So inward, in towards the radius of curvature would be in that direction. And then the binormal, remember you can do the t cross n to give you the direction of the binormal, and the binormal then would be going straight down. So that's how we got the coordinate system on this particle down here. And then the only two forces that we have acting on it, since we don't have friction, are the weight and then the normal force. The normal force has to go perpendicular to the track, so the normal force is going to be going at an angle of theta to the binormal. Remember that in the binormal direction you never can have any acceleration, because you can accelerate in the tangential direction to speed up or slow down. You can accelerate in the normal direction to change your direction to follow the path. But if you accelerate in the binormal direction, that means you're leaving the path. So your acceleration in the binormal always has to be 0. So in the binormal direction, you just have the weight, so mass times 9.81 meters per second squared, and then you have the component of the binormal of that normal force. So this angle is theta, so it's going to be NA, which is your normal force, times cosine of that angle theta, and that's got to equal 0. You can use this then to solve for NA. So NA is going to be the mass times 9.81 meters per second squared divided by cosine of theta. Then we'll do our sum of forces in the normal direction. That's equal to the mass times our acceleration in the normal direction. Oops, and it looks like I dropped the mass. So let me write that back in there. And so that would be the mass times v squared divided by the radius of curvature. Remember, when you have a circular path, that means you have a constant radius of curvature that's just equal to the radius of the path. So our radius of curvature is 200 meters. So we can plug everything in here. So in our normal, the only thing that we have is just this portion of the normal force NA. So it's going to be NA sine of theta, because it's this component down here. And it's going in the positive normal direction, so it's got a positive sign here. And that's equal to the mass times the velocity, which was a given 45.0 meters per second, square that, divided by that 200 meters radius, constant radius. Then we can combine these two by substituting NA using this equation. And then when we do that, we see that we have mass on both sides, so we can cancel out the mass. The 10.125 is just the 45 squared divided by 200. Remember that sine divided by cosine is tangent of theta. Divide through both sides by 9.81, and that gives you tan theta is equal to slightly over 1. And then when you take the inverse tangent, you get an angle of slightly greater than 45 degrees. Thanks for watching.